Subtyping and functors. So let me just say very briefly why that section was there. So I always thought that subtyping was mysterious and somehow complicated and does not fit cleanly into lambda calculus. And I did not know very much about how different systems formulated subtyping, and I don't want to talk about it in the book because I don't know very much about it. What I figured out is that a lot of the practical examples of subtyping can be formulated in a way using conversion functions that are identity functions. Conversion functions that do not actually perform. Hello?
Well, why would you have a conversion function if it's an identity? Isn't that just a real subtype?
It changes the type, it relabels the types, but it does not perform any data transformations.
Okay.
So, for example, it can omit some part of the information.
But then it's not an identity.
No, it's
right.
In some sense, it is still an identity, although subtype is not a subset, and not always a superset, not always a subset. But in some sense, it is an identity function that relabels types. So
I think it may be an identity in the sense that its code is trivial.
Correct. Yeah. In the sense
parameter.
that the code of the compiler does not have to. The compiler doesn't have to put in any computations, any complicated computations, in order to perform this transformation. It's not an identity function because the type signature is not identity. It's it changes one type into another, so it is not an identity function in that sense. But the code is just not changing any data. And for this reason, the compiler can very easily perform this transformation of types, and also it can do it automatically whenever necessary. In Scala, I should add, there is a feature called implicit conversions, where you can just declare a function from any type to any other type, and the compiler will automatically insert that function for you anywhere where you need it to get this other type.
If it can find it,
yeah. If it can find it in scope.
Right.
Now, this is a kind of a abuse of subtyping. You could say, oh, this is also subtyping now. Now anything is a subtype of anything else as long as I declare an implicit conversion function, right? Then I can write code that looks like I'm just calling a function on a different type, right? And
right.
okay, one second. So that's what I'm saying. You can do this in Scala, but this is not what I want to call subtyping. This is kind of abuse of subtyping. It's too powerful. You can perform arbitrary conversions, and just because this feature exists in Scala, it will appear as if one type can be used instead of another. It will appear, but actually it is not reasonable to use that feature with arbitrary transformations. And so in the new Scala 3, they have changed the way that this works, because they decided, well, this is a very strange feature that should be used very occasionally. Anyway, so then I realized that subtyping can be formulated in this way. And then I wrote down some examples, and it appeared to me that subtyping should always be a subset. So I said, okay, great. Let me just prove formally that subtypes are always subsets. That these conversion functions are always injective. Let me just prove that. Okay. So I wrote down the proof, and of course I couldn't prove that. It's wrong. It doesn't hold. And so then I realized that it's not true, and it was very surprising to me.
So why is it not injective?
Because it's for contravariant subtyping, it is surjective.
Well, right, but for covariant.
Yes, so then you have some examples of injective and then other examples of surjective. And then you can take a product of these types, and then you would get neither surjective nor injective. And so it's a total chaos after that. And so then,
like sorry, the traditional example. So you have like points on a plane, on a rectangle. So add color. Will it be a subtype with color? Points with color? Like opinions vary.
yeah, well, you could say a point with color can do everything that a point without color can do, right? And so in this case, in this sense, it is a subtype. But I would say there's a formal.
Turns out that breaks because you want to have if you have equality of points, then
that's right.
Quality of points with color and quality of points without color is different.
Yes, right. But so you could say, okay, you can. So my view on this is that every programming language kind of decides which kinds of subtyping it will support, and that decision is more or less arbitrary. So you can support different kinds of subtyping, I don't know. So I have no opinion about which kind of subtyping is better, and so that's why my book is very light on that. I just want to formulate what subtyping looks like in this case. I want to prove a couple of statements, such as if a function is injective, then you lift it to a functor, it remains injective. Something like that. Right. So that kind of thing I want to prove. And I guess I used this once somewhere else in the book. Anyway. So that's why my section on subtyping is kind of apart from all other sections. It does not connect to other sections very cleanly, and does not get reused very much later on. And so it's kind of, functors have this structure, everything is very coherent, and there is also subtyping if you want to talk about it. That's
question about that, actually.
Yeah.
In the book, it says that, let's see, any type is a subtype of 0.
0 is a subtype of any type.
That's what I would have said. Is that right?
Right.
But I think
Yes,
it occurs more than once. Yeah. Is it just backwards?
Yeah, I noticed that part. That was backwards. I should have.
Okay. Cool. Thank you. That makes more sense.
Yes, made a note. But yes, nothing is a subtype of every type, not a supertype.
Yeah, that's true. If I said that, then I will fix that in the book.
Right, there is a place where you say that, and yeah.
And everything is a subtype of any.
Yeah, but this is a special thing in Scala. So
yeah.
Any is a weird thing. So in a sense, unit should have been the top value in the hierarchy. But saying that anything is a subtype of unit, that's really old. Right? Anyway, that's not what Scala gives you. So Scala has a special thing called any that behaves actually more like a unit than anything else. can't do anything.
It's right. It's got basically two hierarchies in it. Subtyping hierarchy between nothing and any, and then there's sort of the logical subtyping or logical implication between 0 and 1.
Yes.
That's the way I look at it.
I think this is what I brought up last time, but to me, any is the top because it is equal to the predicate true, right? As opposed to the unit. That's why some of the equations do not work. But if we used any as the unit, I mean, as the true, then the logic's, true or something equals true will follow. But if you pick unit as true, then that does not work out. So I'm still not quite sure that unit should be the equivalent of true predicate here.
Yeah,
Right.
yeah.
Well, in some
I
sense,
think it is.
yes, in some sense, the choice is arbitrary. As long as you have a type that you know is always inhabited, it can function as true. And so unit, is always inhabited because there's always a unit. So
I just wanted to see. Do you see that what I'm sharing right now?
Yeah, I have to make
yes.
it bigger, but any.
So
Yeah.
one interesting way of talking about any is that so unit is actually not the same as this interesting type expression here, right? Now this type expression means there is a value of some type, but we don't know what type it is. So
yeah,
somebody
I would actually use the union symbol instead of exists, but
well, I don't know.
In classical, it's all the same thing. So
Yes, but so it's different from unit because in unit there isn't any value of any type other than unit, and there it is. There is inside it. Somebody has put it in. You just don't know what type it is. So, in some sense, it is equivalent to unit because you can't do anything with it. You know it exists, and if somebody asks you for that, you can give it to them, but you cannot use it in any other way. You cannot call any functions on it because you don't know what type it is. And with unit, it's the same. So in some sense, they behave in the same way. So they are kind of observationally equivalent, if that is the right word.
right, you
Because
cannot eliminate unit or cannot eliminate any.
yeah, you cannot eliminate. Well, you can eliminate it, just that you have to ignore it.
Right, you can't. Yes, you can't do anything with it. Can't
You can't eliminate it productively. You can eliminate it in a non-trivial way without ignoring it. So
right, the elimination for unit is just like give the value that you want with no help from the type itself. It's just
yeah. Well, it's and the same is with
DROP.
With the type
Any.
with this type, it's exactly the same. You cannot eliminate it in any way other than just ignore it. You can give it to someone else, and they also cannot do anything with it other than to ignore it. So somebody who created it knew what type it was, but they are long gone, and so they left the company, and they did not leave any private email address. So you can't find it out. So this is an interesting kind of correspondence. So any is more like this than unit, but from the point of view of programs, they are equivalent. So anyway, that's my comment about unit.
Yeah. My comment about any is that sometimes it's used like in like libraries, where you have a hierarchy of things getting more and more specific. And at the top, you don't know what it's going to be. So you have to say, hey, this returns any. But then as you get further and further down the hierarchy, that any gets specialized to a more productive type. But it's like, so you can use it at the lower level, use those functions at the lower level, but if it ever pops up to the top level, it's kind of useless. But that's because you don't know what it's actually doing.
And so subtyping works with any. You have any type T, and then you can map this into the any if you just set A to T. But you don't transform the data in any way. The data remains unchanged. So this is like this identity function that relabels types. So I will probably have to formulate it a little better. Identity function, as we just discussed, it has the code of identity function, but it does relabel the types. So anyway, let me stop sharing.
Yeah, I think in object-oriented programming, for example, like Smalltalk, there is an object and a class hierarchy that are sort of mirror image. I mean, not mirror, but there are two hierarchies because of the principle that everything is an object, A, but then every object is an instance of some class, B. So Smalltalk takes that to the extreme. So in Smalltalk, an object is like the top of the hierarchy, right? Everything is an object, a subtype of the type object. And so that's why, but it has certain properties that every object has to have, like, it's hash code or something like that, maybe equality. And so it does abstract it at that level, I think. Now, in type theory, it's not quite clear because, your representation of there exists A dot A, if that is interpreted as disjunction, then, what is nothing? Is nothing equal to for all A dot A?
Yes.
Okay. And so there is no element that satisfies for all A dot A, basically.
Yeah.
Right?
Right, because A can be null, can be empty.
Yeah, well, I have an intuition for that, which is that for all A dot A means you can produce a value of any type on demand. So it's impossible to write that kind of code.
Yeah.
And you don't know what to produce, and you're not allowed to look into the type at runtime. So this code has to be written in advance, working in the same way for every type, and that is just not possible. And
it has to work for the empty type.
And yes, that is more a mathematical formal objection, right? It has to work for the empty type in the same way that it works for non-empty types. And so if it returns some value, then that value would have been a value of an empty type. So it cannot return any value for that reason. But so yeah, but from the programmer's perspective, it's just impossible to write such a program. So you're right. So for all A dot A is the nothing, and exists A dot A is any.
Yeah, because in practice, I don't know when you would use nothing as a either a parameter or as a return type, right?
You would use it. There are reasons to use it, but not you would not use it as a parameter of a function. You would use it as a type parameter of a function.
Well, see, can I add a comment? So in Scala, you can have a method that that has a return type nothing, and this method, it can be like in the code, it can be called to return so that any variable of any type can be assigned to the value of that method, because this will never happen. So nothing can be cast to any type. That's why, I mean, it's like in our imagination.
Like exceptions return
Yeah,
nothing,
Yes.
right?
But,
So after an exception, it's never gonna get to the code beyond the exception, so that code can do whatever it wants.
or you can pretend that this code returns a value of whatever type you need.
Yeah.
But
There's a concept in I think it's in Haskell. There's something called bottom, which has the symbol like this,
Same thing.
which is it sounds like much the same thing. Yeah.
Right.
yes, yes, yes.
I believe nil for a list is declared as a list of nothing. Is that right? As opposed to being a
No.
list.
That is correct. Yes. So you
Yeah.
use it as a type parameter.
Oh, I see what you're saying.
So
Okay.
because it's a subtype of any type, yes, you don't have to declare a type parameter for nil. You just declare it as being of nothing.
And then you use subtype.
But then you have to make sure that list is declared as covariant.
Yes, yes. And I actually have a doubt that it was a good idea to require programmers to declare things as covariant or contravariant, because functors or type constructors are covariant not because you declared them to be, but because they are or are not. And so
Right.
list, for example, is defined in some way, and it is covariant. You can define, you can pretend that it is not for the purposes of your code. But this would be, I'm not sure why how useful that is. You have a type such as option in Scala, right? Option is declared as covariant because Scala requires you to declare it. Why? So why don't you have a programming language that automatically figures out covariance?
But that programming language is Scala in the sense that Scala checks covariant annotation. It knows whether or not covariance applies. But when you are passing around type constructors, you need to know whether their parameters are covariant or contravariant. And if it's an arbitrary type constructor, then you cannot, you cannot tell whether.
Okay, I understand.
Yes.
I understand that. But why do I have to declare this for option? If the compiler already knows that it is covariant. What is the point of giving me the possibility to not declare it as covariant and prohibit me from doing something in my code? Is that useful? Anyway, so I'm not sure.
Right.
I don't know. It's kind of like part of the type in a sense. It's like, by declaring it there, then you avoid certain errors. Like if you then add another method and it turns out that it breaks covariance, then
yes, you change the declaration in some way so that it no longer applies. You will get the warning at the site where the change was, and not where you tried to use the type in some context that expected it to have a covariant parameter.
Okay, yeah, I guess that makes sense.
I think, the covariance and contravariance in object-oriented programming has always been a puzzling thing for me, because languages like Java, they do not have covariance in subtyping.
Excuse me, Java does have covariance, and I remember that somewhere like between Java 5 and Java 6, covariance was introduced in some like classes
for arrays,
map or something, map or list. So it was not so it's a hidden covariance, so they don't declare
okay
it. They became covariant.
Right.
I mean, like
because
class map.
there are languages like Eiffel that allowed covariance. And the problem with covariance is that once you have one class method that's covariant, then you have the compiler has to basically check the whole universe to make sure that that covariance does not violate use of some of that class somewhere in the code base. And so that's why the compile speed of Eiffel and Scala, because of the covariance, is so slow. Whereas in a language that does not allow covariance, all you have to do is compile that method in that one class. Nothing else in the universe will be violated by having a contravariant something. And so I'm not sure if Scala, requiring it to be declared covariant may be related to that efficiency of the compiler, that the compiler can assume something.
Right. Otherwise, at a
Right.
modular boundary, you would have to cross that boundary and check every use.
Yes, yes.
But
You
if
have
you
to-
Well, see, actually, Scala as a language appeared because when Martin introduced parameterized types, he discovered later, and it was too late, that he discovered that he had to have covariance, had to have variance declared. So that's why he declared like a flavor of Java with variance. And then that's how it all started. So in Scala, you like declare variance explicitly.
Mhm.
Well, and currently there are opinions that maybe it was not a very bright idea. It was long ago.
Yeah, I mean, I've programmed in Eiffel, which allows covariance.
Mhm.
And there are a few times where, like an array of A is a subtype of array of B, if and only if B is a subtype of A. That's the one case of covariance. But it's not clear. The rest of the world, the rest of the code, you never really need covariance. Contravariance is more natural. And that's why, Java, C#.
But wait, but you cannot have one without the other. You cannot just have covariance without having
Yes.
contravariance, or vice versa.
Yes, you can. Java, you cannot declare a covariance, because when you have a method that's a subclass, then the types have to have the contravariance signature. The compiler will reject if it's not. So yeah, but it makes the compiling much more local, so and faster compared to Eiffel or Scala. That's yeah.
I don't know about that. So why do you say that at a subclass it has to be contravariant? I don't know what you're talking.
Because then you can always use a subclass wherever the class is. But if it's covariant, then it may be the case that some attribute that you expect will not be in the subclass. You see, you're not guaranteed that. So, yeah.
Well, yeah, I kind of agree, kind of like what Sergey was saying. You sort of need both. We're talking about the annotations, right? So you have a covariant annotation and a contravariant, and sometimes like you get functions, and for a function to be covariant, the parameter has to be contravariant. So, you need to have both and specify them correctly.
If you don't have, that's right. So also what I found while working on this particular chapter 6, what I found is that constructions require you to talk about covariant and contravariant at the same time. So, for example, if I wanted to determine if a given type constructor is covariant, and this type constructor is allowed to have products, co-products, and function types. Then I must be also able to determine if some type constructor is contravariant, because one of the construction is that just what Peter was saying, a function from A to B, where A is a contravariant type expression, then it becomes covariant, right? So a function from A to B where A is covariant and B is contravariant, that becomes contravariant. So you have to, when you define polarity or covariance, contravariance, you have to define it once, covariant and contravariant constructors. You cannot just define one fully and then define the other. So a programming language where you are allowed to denote one but not allowed to denote the other, that would be a very weird thing to me. It's like somebody didn't think it's true, because you cannot really check or determine if some type constructor is covariant if you can't even talk about type constructors being contravariant.
Yeah.
So let me show you what I mean here. Oh, everything is gone. Okay, good. So for example, in Scala, you can say f plus a, right? And you can say g minus a. And you can denote it like this. And then if you say, for example, h of a, you can define, right? So type h of a equals f of a function to g of a. Right? Then h becomes contravariant. So you can do that, and the compiler will check that this is true. So this is covariant, this is contravariant. And the result is contravariant. So if you want to say, when is this contravariant, you have to be able to say that something else is covariant. When you say that, if you want to say that this is contravariant, you must be able to say that this is covariant. So there must be some notation for that, and you must be able to check for that. So you cannot have a language. Well, you could, but it would be very strange to have a language where you can denote one, but it cannot denote the other. Because then constructions like this will not be able to be checked. And that kind of defeats the whole purpose of having that annotation, because the compiler should be able to check.
Right. It would make sense only in a language where functions had output types, but no input types. That would be very strange indeed.
Right. And so, by the way, Scala does not have libraries right now that automatically produce this information from type. Scala has a library called cats, right? And it has automatic derivation of functor and contravariant functor instances. Sorry, not contravariant, only covariant functor instances, and only for polynomial functors. So it does not deal with this sort of situation. And so, as far as I know right now, Scala does not have any library that allows you to automatically derive a functor type class instance or a contravariant type class instance for an arbitrary type expression. And that's a pity. So it's something that I think is missing in the ecosystem. And it is present in Haskell. In Haskell, you can just say derive functor. But in Scala, you cannot. In chapter 6, I show that this is a completely mechanical process. So if I give you some type expression like this, K of A equals option of A going to some I don't know what, and comma, something else, doesn't matter, right? So whatever I write, some kind of type expression, I can determine automatically that this is, for example, contravariant in A and covariant in R. What I would like to do, for example, is I would like to derive automatically the functor instance or the fmap method for this type with respect to the type parameter R, which is covariant, and a contramap method with respect to type parameter A. So R to S, KAR, KAS, and B to A, KAR to BR. So I'm using now my notation that essentially omits the square brackets, puts it in the superscript. So I would like to derive the code of fmap and cmap automatically. I don't want to have to write it by hand. And this is a completely mechanical derivation, as chapter 6 shows. Any questions or comments on this?
Yeah, I think whenever I look at the function constructor, like in the definition of H, I translate it into not FA or G of A, because I see the not is the one that flips the contra and so on. And that's why, yeah, when you have a covariance on the F, but then it's the negative F of A, then that flips the covariance to contra and so forth. So that's why when you do that nesting, then it flips back and forth. So
right.
yeah,
right.
I see that.
And if you have things like A to R to S, C, and you flip multiple times.
Yes, yeah. That's why A can be in contra or covariant position, depending on how deeply nested it is. Yeah. So, yeah.
You count how many arrows it is to the left of.
Yeah, but the arrows need to be nested because it's not the same
Right.
as this. Right. So if you have this, for example, then
Right.
it's not
Yeah.
the same.
Right.
Yeah.
Yeah, I found that confusing because there's an example in the book where the type A occurred to the left of one arrow, but to the right of another arrow.
Yeah.
I'm like, okay, what do you do in that case? And I think then what you have to do is remember where the parentheses go.
Yeah. Well, this
Right.
I comment on it in the book. There is an example where this is explained. Maybe this is just one place where this is done, but yeah, certainly this is an important point. So this one, for example, this R here. This R here is in a covariant position, actually. And this A here is also in a covariant position. Because this is equivalent to that.
Yeah.
By uncurry. So you have to mentally uncurry before you apply this logic.
Yeah.
It's contravariant within the parentheses, but then The
Yes.
extra arrow T on the outside makes it covariant again.
Yes.
Is that right? Okay.
That's right. That's right.
Of
And,
course, it's
yeah.
possible for a type parameter to appear non-variantly, that is, in both covariant and contravariant positions.
Yes. Certainly. Yes. You can have things
A arrow, A.
Yes.
like that. That's yeah. You can have all kinds of things like that. But quite importantly, even in this case, some positions will be covariant and others contravariant. There are no positions that are neither.
Right.
And that's very important because that allows you to classify everything. So even in this case, some positions here, this is a covariant position, and this is a covariant position, and this is a contravariant position. And so you could just say somebody should disambiguate this type into something like that, where each type parameter occurs only in a specific variance. And then let's call this P of AB, right? And then if you want this one, you just use P of AA. But the properties of P are simpler.
Yes.
Because each type parameter of P has a specific variance. And so properties of P are simpler to think about. And then if you want to use this one, then you just use P of AA. And so that is actually quite an important property of this sort of lambda calculus, that every parameter position is either covariant or contravariant. And this is automatically determined, it's mechanically determined. So there's a very simple counting to be done, and you can automatically determine this, for example, in a Scala macro, you can do that at compile time. And in principle, you could write a library that performs this kind of computation, and certainly Scala compiler does. But you could perform a computation to derive the code of these functions automatically. So that
You're talking about the code of FMAP?
Yeah, code of FMAP
okay.
and CMAP. So P of AB is covariant with respect to A and contravariant with respect to B. And you could automatically derive the FMAP and CMAP for it. And that is good enough for pretty much all purposes working with it. And then you can go over to here and see what you can do.
I think, yeah, that's right. One of the reasons I think for having the variance annotations on the functors is that sometimes you then use them in another expression. So instead of saying A arrow A, maybe it was A arrow Q of A, arrow A.
Yeah.
But if you don't know what the variance of Q is, then everything you just said doesn't work anymore, because
Right.
you don't know what a Q of A is, whether it's plus or minus, and then you're screwed. But if you know the variance of Q, then you can continue with this process.
That's right.
And trying to in that case, trying to compute those things may mean that if you don't have the variance annotations, you'd have to kind of go back and figure out what the variance of Q is while you're working on this one.
Yes, that's true. And then I suppose that's recursive. So we'll go back.
Yeah, I guess that could make it tricky.
Yeah, I wanted to make a comment here, which is that when you have a type constructor with multiple type parameters, then this sort of consideration applies separately to each type parameter.
Mhm.
with all others fixed. And then I have a section, I believe, in chapter 6 about bifunctors. I'm not sure if anyone actually looked at this.
Haven't gotten there.
But bifunctors are type constructors with two type parameters that are covariant separately with respect to each one. But actually, that is not how bifunctors are usually defined. And the reason is there must be, so let me actually go to a different page here. If you have a bifunctor, say f of AB, it's a plus A plus B, right? You can map it with respect to the first type parameter. Say call it A prime B. Or you can map it with respect to the second type parameter, right? And then you map it to A prime B prime in two different ways. And so you first use fmap with respect to one type parameter, and then you use fmap with respect to the second type parameter. So to speak. Right, so and this has to commute. Right. So now this is a law of commutativity for bifunctors. And this law follows from parametricity for bifunctors defined using purely parametric code. But this is not trivial. This should hold, right? Because you in the consideration in here, you're looking at one parameter at a time. So you can easily determine that one parameter is in a covariant position. Then you can determine that another parameter is in a covariant or contravariant position. But this does not give you any information about whether this kind of law could be satisfied. So just looking at one parameter at a time is not the same as requiring that these two fmap functions somehow commute. So this is a non-trivial statement, in fact, that requires proof, which is not easy. So I put this proof into the appendix because I just thought this is kind of time-consuming to do this in the chapter. Anyway, let me stop this and ask for other questions. So did anyone notice anything else?
Just one comment in that diagram, the commuting square.
Yeah.
Don't you need some function of a prototype, or
Yes.
because
Yes.
in page, yeah, okay, you left that out.
You want to share the screen?
Oh,
You're looking at specific page.
yeah, sure, I'll share the screen. I don't know. Can you guys see it? Is it too small?
I can see it.
Yeah, it's okay.
Okay. Yeah, this diagram here is what you just drew, and there is this F from A into C, G has to be supplied. So yeah,
Yes.
that was my comment. Because it looked,
Yes.
the functor application was, okay, that's it.
Yes, of course. Yeah, you have two different functions from A to C and from B to D.
Mhm. Right.
And so you use the by map kind of to do this transformation at once
Mhm.
between FAB and FCD. You change both type parameters at once. But actually, if you just looked at the type constructor with respect to each type parameter separately, you do not have by map. You have only F maps with respect to each type parameter separately. So you have F map of F dot B, and you have an F map of F A comma dot. You don't have a by map. So you could either say that you are required to have a by map, but then you need extra composition law of by map that you need to check. Or you just say parametricity, save me from all this. And parametricity comes and saves you and guarantees that this law holds. So, yeah, so like I give this example of the bifunctor A cross B cross B. Very, very simple. And commutativity law holds for it. You map A and you map B separately, but they are independent of each other. So now the question is to prove that this is always the case, even for complicated type expressions. That the commutativity law will always hold. This diagram always commutes. And similarly, if the type constructor is covariant with respect to some type parameters and contravariant with respect to other type parameters, and you have F map for some type parameters and C map for other type parameters. But still they all commute always. So no matter how many you have, and whether they're covariant or contravariant, they always commute.
Question?
Yeah.
I've only really read up to section 6.1, so I might have missed this, but you said that you say that F map is fully parametric, I guess.
Yeah.
Did we prove that? How do we know that?
Well, so we don't know that, right? Because we don't know what F map is. Where does it come from? Who gave us that, right? So if we derived F map, so now if you look at the table of contents, there's section 623 and 624. Constructions of functors, constructions of contrafunctors, right? So this section shows you how to construct F map for any type expression that is made up of products, coproducts, and function types, exponentials, right? So step by step, and then if you look at, I think section, yeah, so these type constructions, if you look at section 625, maybe you will see, yeah, the solve, can you scroll down, please? If you look at that, Yeah, so then there's an example of how to determine the covariance or contravariance. And then there's an example, if you scroll down to the next page, is example 6252. Yeah, so this is, this shows you, so there's a type constructor, right, given in example 6251, which is a very artificial type constructor, you know, int plus a, 1 plus z to int to z to int, whatever, right? So that kind of thing is covariant with respect to a, and contravariant with respect to z. And so you want to automatically build up the fmap. So in order to do that, you decompose the type into the elementary steps, like coproduct, exponential product, and so on. And for each one of them, you know how to construct fmap for the larger type if you know fmaps for the smaller types, or cmap, whatever that's necessary. And so in this way, you have a procedure that builds up fmap or cmap as appropriate. And that procedure is guaranteed to give you a fully parametric code.
Okay, so in that
Right.
context, we can rely on.
So if you use that procedure to construct fmap, then you are guaranteed to have both fully parametric code and laws holding, all laws holding.
Does it work the other way? If you have a functor and all you know about it is that the laws hold, does that mean it's fully parametric?
So I don't.
Does parametricity follow from the laws?
So,
Okay.
For the functors, there is the functor laws follow from parametricity. So if you have parametricity, if somebody tells you, I have an fmap of this type signature and it is fully parametric, you can derive the composition law of the functor, and you can derive the, I believe you can even derive the identity law, I'm not sure. Composition law for sure you can derive. So, but I'm not sure you can derive the other way around. If somebody gives you a function that just satisfies the functor laws, right? Is it fully parametric? Well, you don't know. I mean, it will satisfy all the laws as if it is fully parametric, but who knows what's inside it? You know, maybe it has side effects inside it. You know. So I mean, I'm just saying I don't have a proof. I don't think anybody has that proof that if the functor laws hold, then it is the naturality law also holds, or it is fully parametric. I don't know if that's, I'm not sure. But I do have a section in an appendix that talks about it to prove that. So what you can prove is that there is only one implementation of fmap that is fully parametric. If an implementation is known to be fully parametric, then that's unique. That you can prove. And this procedure, which is shown in this chapter, gives you a fully parametric fmap and cmap. So it is constructing this unique existing fully parametric code for fmap and cmap. And this is actually very important, that there's only one implementation of the functor type class that is fully parametric. I don't think there are any examples where you have alternative non-fully parametric implementations that satisfy the laws. I don't know any such examples.
So when you say it's fully parametric, that's based on sort of the syntax of the thing, right? it's not like,
So for example, the
Yeah.
type int, which is in this 6251, right? It has type parameters A and Z, but also it uses the type int, which is a
Mhm.
specific non-parametric type.
mhm,
So, but the code of fmap uses int as if it were a type parameter.
mhm,
It does not insert any values of type int anywhere. It does not use any functions specific to int. For example, increment some of these values or anything like that. It's if you go through
mhm,
the next page is the code of this function of the fmap. Then it does not. It treats values of type int as if those are values of some completely unknown type. As if essentially int is another type parameter that is held fixed. That is what fully parametric requires you to do. So you're not allowed to use specific values of type int in here. As if you do, essentially you will violate the laws.
mhm.
Right. So the only function that can appear is the identity, basically, right?
Yeah.
Yeah.
It is the identity, or you can apply one function to another, or there are constructions that you're allowed to use in fully parametric code. You can build up code from these parts. So you can, for example, you can have a case match expression. You can have constructor of a disjunctive type, like you can construct left and right of an ether, and so on. So you're allowed to do that. You're allowed to take a tuple and extract one part of it. You're allowed to take some values and put them into a tuple, and so on. That's what you're allowed to do. So the code, if you scroll down just one page, you will see the code of this function, fmapg, in the code example. So this code uses standard map methods for either an option, which are fully parametric, and then adjust some stuff, like take destructuring a tuple, apply functions to arguments, put values into a tuple, and so on and so on. So that's fully parametric. So none of this depends on specific values of integer type. None of this calls functions that depend on specific types or something like that. So int could be just as well a type parameter in this code. And this wouldn't have changed anything. If you just if you just replace int by type parameter I, then it will be exactly the same. The code will not change. So that is so this is what I mean. So this procedure is entirely mechanical. It looks at the type of your type constructor and produces this code as a big lambda term in fully parametric way.
I guess when I see something like this, I wonder about, in practice, this is related to the the theorems for free kind of a thing, right?
Mhm.
The structural shape of product and function and so forth. allows you to derive certain things like this. But I just don't see the usefulness of this in actual programming, right? When you're, because you have to deal with values, you have to deal with properties of specific functions and so on. Like, I guess what percentage of a practical application consists of code that deals strictly with FMAP in its full generality? Because we use FMAP in Scala all the time, but we don't spend that much time creating new types that are very complicated beyond the usual thing. So
That's true. That's true. That's true. Now, but you sometimes have custom data types that have type parameters. Right?
Yes.
Usually
Sure.
they're simple. They're not very complicated, but you do have them.
Yeah.
And for Adrian?
Yes, you do have them. I have certainly created data types for which I have implemented an FMAP. So it may not happen that often, but the whole point of talking about these laws from the point of view of a practical programmer is that if you don't follow the laws and you mix up your FMAP with the FMAPs of other data types, as you often do when you're manipulating a big data structure, and you have a bug in your FMAP such that it doesn't follow the laws, that's going to be hard to track down because you're going to get very weird behavior and you're not going to know why. And so, yes, I think all of this discussion of the laws governing functors is indeed useful to the practical program.
Yeah, so what I would like is that if you have a custom data type with a type parameter, then you would derive FMAP for it automatically. Right now, the CATS library can do this for you if your type is polynomial, but not for any more complicated, and certainly not for contravariant types. So,
right, not for function.
Not for function. Like exercise 6311 is about contravariant contrafunctor that has a CMAP method. Now, none of the libraries that I know can derive this kind of code, but this is still just as mechanical as the FMAP for polynomial types. It's just that there's a bit of this complicated higher order function that you have to write. But none of this is kind of, it doesn't require any thinking. It's a mechanical procedure, which is very quick. So yeah, now how often you would do that, I don't know. I certainly agree that in most programs, this is not very often. One second, please.
Yeah, I think what's, now that I'm thinking about this, it seems like for the practical purposes, the data types that we construct are usually first order algebras, right? We define set of elements and then we define operations that take elements to other elements. We rarely define a higher order data type which can take an arbitrary function, right? Most algebras that we deal with in mathematics, for example, they're not high order, they're all first order, right? Yeah. And I'm trying to think when would we use high order? When do we create an algebra that says, map like higher order objects are defined? And that's a good question. That I'm wondering. If we had this machinery, then maybe we will start thinking about data types as more than first order, higher order.
Yeah, well, there's a question. Sorry, Peter.
Well, it's just exactly what I was wondering what means by higher order. I mean,
Higher order functions.
there are, you could say like list of A. Well, list actually for any A, list of A is actually an algebra, right?
Right.
And
right.
so it's just a parameterized algebra. But is that what you mean, or is there something more?
Yeah, I'm thinking the algebra itself. We have operations that take elements of the algebra into new elements of the algebra, right? Do we have an
Mhm.
algebra where functions themselves are part of that algebra, right?
Oh,
That's not
I,
the
I
first
would
order.
have
And
to jump
like,
off
is F
for some time.
is F
Sorry.
map a part of the algebra, or is it part of the
No,
kind of
it's not.
the?
No, it's separate. It's separate.
It's
not
separate,
part of
right?
this,
Yeah, yeah.
No, but let me just say one thing. There's a Stack Overflow question somewhere about the usefulness of higher order functions. How do
Okay.
you? Now, there are some very rare examples where you do need higher order functions of higher, something about parsing. I can't really tell you in detail. But anyway, I need to drop off for some time. So
Okay.
All right.
Thanks.
I don't know how relevant this is, but I mean, people do think about continuations, right? Doesn't a continuation have 2 arrows in it?
Continuation.
I don't think about them, but I know that some people do. It is a term, right? So people are interested in them for the purposes of programming, I think.
Yes, if you're reifying continuation, yes, then it's the type is definitely a function. So you're thinking, I see.
Well,
Yeah.
it's just an example that is higher order, right? That's I think in the sense
Definitely. Yeah, definitely.
Explain that to me. You're saying that the continuation type is higher order, or the actual continuation? I don't know, because I mean, I guess I'd have to see the type of it, but I imagine it's just a parameterized type, right?
Well, maybe we shouldn't use the word higher order there. I mean, a continuation is a function, right?
Right.
So the question is,
and it's a function of a specific type.
Right.
Type.
But do we have cases where we are passing a continuation, right? Explicitly, then that function will be a higher order function. And I guess the question is, do continuations, can they be considered a data type in some algebra, like the algebra of a language with reals and integers and continuations as a basic building block of that language is types? And I don't know. It's used for compiler interpreter definitions because of control flow. But I'm trying to think of Scheme, which has the continuation as a thing that you can grab hold of. But in normal programming, I mean, yes, I guess it's related to exceptions, right? Like exceptions are, in a sense, a continuation, except they're kind of implicit because they break the flow of control outside of the regular evaluation order.
Right. I mean, it seems like you can create a class where the constructor, takes a function as, one of its arguments, and, that class itself kind of forms an algebra. It's just like some of the values happen to be functions.
Mm-hmm.
It's operating over some sort of basically it's operating over a tuple of, say, an int and a, I don't know, int to string function or something like that, you know.
Yeah, but
I'd have to
when,
write down an example, but I mean, the point is just having functions that take functions. I think that's pretty much core idea of functional programming.
yes, it is. I guess the question was, Sergey was saying that in cats, they allow polynomial type constructors, but
Mhm.
not function. And my question was, I
Mm.
wonder if that's because we normally think of data types as algebras as just first order and not higher order objects. And the question is, what would be a higher order data type besides the, we have the hierarchy of functions over things, right? Once we have functions, but do we think of that as a data type? I'm kind of fuzzy here. I mean, obviously, I'm rambling.
Yeah, I'm not sure.
Because most of the time, like, for example, in Scala, if you define a new class, let's say, right, you define functions within it that take,
Mhm.
objects to objects, etc. Do you also declare higher order things, higher order functions that are specific to that class? Or are we assuming like composition is a given, right?
So isn't fmap itself a higher order function? I mean, it takes a function as an
Yes.
argument.
Yes,
So,
and compose, for example, is a higher order.
right. So, you might very well have a class with a fmap in it.
Yeah.
Or am I missing something? I mean, it just seems like, yeah, that's
Okay.
having higher order functions, but I don't know what that breaks anything.
Right.
I just
Well,
think
the automatic
functions is just another kind of data type.
the auto generation, I guess, of the methods or the functions that cats apparently provides. If the functor is polynomial, defined polynomially, then you can automatically derive all the the standard, what is it, I don't know, the thing that Sergey was talking about. You can derive,
Right.
you can give explicit code to
Functors.
implement all the components. Yeah.
Yes.
But with function, once you introduce a function, then maybe there's a threshold that you cannot do it automatically without
No,
more
I think that's not the
information.
case. I think he's just saying they haven't done it.
Okay, they haven't done it.
Because they haven't gotten around to it, or they have limited ambitions or whatever. But it's not because there's no way to do it in principle.
Right. Not in principle, but I'm just wondering if that's because in practice we don't feel the need for it. So that's my question, right?
Right. It sounds as if Sergey has felt the need for it, or at least has noticed that it's missing. So,
Yeah. Right. I mean, it's kind of like dependent types in general, right? Most languages don't allow you to do that, even though it seems like a mirror image of Cartesian product. So, why not? But it's in practice.
right. Well, it's work for the implementers, what it is.
Yeah.
So, yeah, speaking of dependent types, looking through this chapter, it seems like this is basically a specification for a dependently typed functor library, where the library includes all of the relevant proofs. That is, all of the properties that you would want of a functor are provable by the techniques that he is using here, and you just need to translate those into a dependently typed language. And I don't know that any Ogda library actually does that, but they ought to do it.
You mean like derive fmap? Is that what we're talking about?
No, what I mean, do they have basically type classes for something like functor that include all of the relevant proofs so that you know that your functors are actually well behaved and lawful?
Oh, yeah.
And yes, you can certainly do that in principle. Has anyone actually done it? I don't know.
Yeah, I'm not sure. I'm just picturing, I'd have to go and look, but I think there are like some of, when you go down into the libraries and look at some of these things, like what for functor, then, they do mention the laws and they do express them formally, but I don't know that it's actually part of the so-called type class or not. I don't know
Right.
that you have to specify the laws. You don't have to prove the laws for your functor necessarily.
Right, I'm very
Call it a
unfamiliar
functor.
with the libraries. So, and I guess there are quite a number of them. There's, the basic library that ships with Ogda is not very complete. So people have rolled their own, but I don't really know what's out there.
I guess I wonder what is the right answer for a programming language? Do you, like, if you have a dependently typed language, do you require people, and you put laws on things, do you require people to, programmers to implement the laws for all their things, or?
Well, I think there are things.
Or you don't have the laws, or it's sort of more in the optional area?
I think it's a mandatory option in the sense that there are things that look syntactically like functors, but are not well behaved. And sometimes you might actually want such a thing, but you should choose it explicitly when you do that. So there should be essentially two versions of the functor type class. So you've got a pseudo functor, which has an fmap, but the fmap doesn't obey any laws. And as a built upon that, you have a lawful functor.
Right.
Right. And so you have to choose when you are implementing something, is it a functor or is it just a pseudo functor? And by doing so, you can document whether the thing is going to play nicely or not.
Right. And of course, the full functor, the verified functor, might require, in its definition, if it calls other functors, then it would require that all those other functors are verified, whereas just what you're calling the pseudo functor wouldn't have to.
Right.
So, yeah. I'm thinking of sort of like the lawful functors being like basically a subclass or a subtype of the just pseudo functors.
Right. Yes. Right. That is the idea. So then I guess the question is, do we have any other things to bring up about this chapter, which I think is mostly very, clear and explicit.
I mean, I have things that, I think might help improve the description, the explanations of things, but
Yeah, I was
they're
wondering about.
not too important. Go ahead.
Yeah, I
Neil?
mean, I was curious. Oops. Yeah. The use of the word functor seems to have, become a meme in programming language, but not natural transformation. And to me, there is an implicit natural transformation underlying these laws, right? Like, or am I just trying to, bring category theory into this? Because to me, natural transformations are, I mean, as McLean said, the whole point of functor category is to define functors, and the whole point of functors was to clarify the definition of natural transformation, where the naturality of one construction like F and another construction G, right? That there is a natural way of mapping from one G to another F, for example. And to me, the power of all these constructions like the algebraic, the polynomial, etc., is so that you can represent something into something else, right? That's, to me, that's the power. But he's doing that implicitly, I think, by well, maybe he's not. So far, it seems like he's doing the algebra of functors using the plus times and function.
Right.
But to me, the more fun thing would be, when are two functors, naturally, what can I transform one to another, right? Like simplifying something or different representation, etc. So
We talked about that a little bit in
I-
chapter 5, right? Because there was a thing about when two types are equivalent.
yeah, maybe.
Presumably that would be an isomorphism, like a natural isomorphism, probably.
Right.
My understanding is that in a language like Haskell, certainly any kind of function between functors has to be natural. It's just part of the parametricity of the language forces it to be natural.
Right,
I see. Okay.
right.
Okay.
But Sergey isn't saying that, and I think that's because he explicitly wants to avoid category theoretic language to keep from intimidating.
Yes, I understand that.
But
But
for people who know category theory, it should be easy to spot, category theoretic concepts in this book.
yeah. So when he writes, for example, one arrow A is isomorphic to A, right? Is that a natural transformation, basically, right? Natural isomorphism, right?
Yeah.
I think so.
Okay. Yeah. So it's implicit in his, when two types are equivalent. Okay. It's just that he doesn't say that. Yeah.
The other thing that strikes me is that
Hmm.
natural transformation is basically, you should suspect there's one of those whenever you see a commutative square. And we haven't seen a lot of commutative squares, but there is one there for the bifunctor, right?
Right.
I don't know whether that's should productively be regarded as a natural transformation, but you might want to give it a try at least.
Yeah.
Hmm. I mean, with the one arrow A being equivalent to A, he gives the functions that go in each direction, but
Yes.
I don't know that he ever proves the commutivity, condition, the naturality square. Again, I think
Right.
it just follows probably from
The
the fact that the
parametricity.
language is parametric, but I don't know.
Right.
Yeah.
Yeah. So yeah, so if there's an isomorphism between any A, then that's natural. So yeah. Okay. Yeah. I mean, by implicitly, right, the fact that A and B are anything, we are being, natural over A and natural over B. So
Right.
okay.
So yes, I mean,
Right. But this is
Actually-
all one functor.
Right. The same functor.
Right.
Yeah. So yeah, I'm just curious.
yeah, I mean, I think it might be kind of fun, if Sergey had footnotes that were legible only to people who knew category theory. Maybe you
think that
have
would be-
some-
That would be fine to put it in appendix or something, right? Because it's
Yes,
not going to scare anyone away if it's in an appendix, and it might be interesting for some of us.
yes.
Mhm.
Yeah.
Yeah, Emily Real in her category theory book, occasionally she'd be doing stuff and then footnote, and it's like, if you know something about, manifolds over blah, 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 then this means this, And it's like, I'm glad that wasn't in the main text.
But if you don't know that, don't worry about it. It's no problem.
Don't worry about it. Yeah.
Yeah. I mean, this book is pretty heavy going for the average programmer. Okay. I mean, a whole like 100 pages or 50 pages on functors and contravariant functors. I guess, yeah. There's a book called Functional Programming in Scala. And it is much, much, much more, simplified. And yet people have complained that it has too much because the authors are coming from category theory or Haskell, and they're trying to make Scala into a Haskell. And
They
people have
abandoned
complained.
Scala now,
Did they abandon Scala?
Yeah,
What
they
are
have
they-
their own language. Like if you look up what Runner is doing, so.
Okay.
But
Yeah, they
anyway,
wanted-
like in Madrid Scala meetup, they have this slogan: "Quema el libro rojo," burn the red book. And frankly, I
And the
would
red
say,
book
like,
is the programming.
yeah, this functional
the
programming
functional
in
programming.
Scala. And I
Right.
would say basically when I bump into like some mathematical errors, I just stop reading. So it's cool, like it's a good exercise in like deep things, but well, you have to be stricter.
Right.
But it's
This,
a nice, funny reading.
sorry. This meetup group worked through that book some years ago. So,
Oh, you did?
We did?
Okay.
Oh.
right.
That was before my time.
I don't remember how many of us were actually around for that, but it's the thing we did.
Just speaking of our group, the Monday dependent typing track, the paper we're reading now actually sort of has quite a bit of category theory in it. So it's almost like we're doing more category theory in that track and more programming languages in this track. So it's kind of flipped in a way.
Yes, you might always almost be led to think that there's a connection between them.
Yeah.
That each one keeps appearing
Yeah.
in the other. Yes.
Yeah, the two of you are basically the common denominator. So
I don't
yeah,
know. I think everybody is in fact.
I looked at your recent reading that you guys are kind of doing, and I'm thinking, no, this is just too much for me. I can't handle it.
Did you look?
This
Is
meetup?
it the universe paper? Is that the one you looked
Yes.
at? The general.
Yes.
Yeah.
I mean, the Mala universes and the various different, recursive ordinal hierarchies. I don't know. You know my
Right.
feeling about set theory, so
The whole point is that this reading is actually too much for us as well. We're trying to figure out what is going on. So it is not like reading this book where most of the material is familiar with occasional surprises. Those papers are almost all incomprehensible with occasional brief moments where we can recognize something. So
Yeah, I took a day to figure out like the first definition, you know, it's like maybe that long on the page. It's part of a page, and it took a long time to decode it, and I'm not even sure I got it right. So I can't go through the whole paper doing that. That was just too much.
it is.
wow.
As you do that, you do, I mean, sometimes trying to figure out one thing takes you pretty far afield, and you do learn stuff. So so that's why we're doing it.
Yeah.
Is it going to be applicable to the programming language that you're developing, or dependent type theory?
Right. I don't know that anybody but Ben is developing a language, but I think it's applicable to what he's doing, because he wants to know what the theoretical foundation is of how his
The relative. Okay, so that particular paper is not talking about the relative proof strength of the language, or is it related to that?
Well, insofar as I guess universes are related to infinities and infinities are related to proof strength, but it's not directly talking about proof. No.
Okay.
Yeah.
It's more about making universes sort of first-class objects rather than something special or on the side, I guess.
And how to avoid Russell's paradox. Yeah.
Yes. Or any other sources of inconsistency.
Right. Well, good luck.
Yes.
So we're getting towards the end. Do we want to think about like when our next meeting is, and what the topic is?
We should think about that. So I noticed that chapter 7 is very short. It's just a discussion of notation. So what if we did chapters 7 and 8, 8 being much longer, which type classes, functions of types. So I haven't looked at it, but that sounds interesting. Semigroups, monoids, pointed functors, pointed contrafunctors.
I'm willing to give that a try, but I still haven't finished chapter 6. So I think if we do that, I will not likely finish chapter 8. Just so you know, I will probably read a bit of it.
Yes, chapter 8 looks very long, and quite honestly, I might not finish it either. But
so maybe we'll say we'll finish with chapter 6, do 7, and start on 8 or something.
Yeah, go as far on 8 as we can. So as far as the timing of that meeting, both the Saturday before and the Saturday after Thanksgiving are bad for me. So that puts us.
And I assume Thanksgiving is bad for some people.
Yeah, well, Thanksgiving Day, we don't usually meet on a Thursday, but the Saturday after Thanksgiving is bad for me. So the next.
Oh, never mind. Yeah.
The next slot would be the 3rd of December. Is that?
It's okay to me.
Awesome.
I have a conflict on that for
okay.
about an hour, but I have another meetup that's from 9 to 11 on that Monday. I mean, on that Saturday, but that's okay. I mean, you guys can continue.
Or we could move it to the 10th.
So Adrian, you're saying you have a problem with the 26th?
Yes,
Okay, all right.
Friends over Thanksgiving weekend, and
All right, we could do the 10th. It gives
Yeah.
us more time to get into chapter 8.
chapter 8. Yes, it might take us a whole month to chapter 8. Okay, so 10th of December sounds like a plan.
Okay.
All right, well, thanks very much, and until next time.
Thank
All
you.
right.
And Sergey, sorry you
Thanks,
didn't get to
Tom.
come back,
Yeah,
but bye.
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 Good having you, Vlad.